Okay. And in a battery, where does reduction occur? Does it occur in the cathode or the anode? Okay, let me give you a hint. Red cat eats a dog. So where does this occur, in the cathode or the anode? Yeah, so you can actually write E cathode here. And what does that not, that little O superscript represent? It represents standard state. Okay, so that's the second thing I want you to know. The first thing I want you to know is that these numbers never change. Okay, you will never change these numbers. What can you change, though? The sign, okay? Okay, and how will you change the sign? You're flipping the half reaction. If you flip the half reaction, Leslie, it no longer becomes reduction. What will it become? The opposite of reduction, which is oxidation. Okay, so red cat eats an ox. So if you flip a reaction, you flip the sign, it becomes now what? Oxidation. And where does oxidation happen in a cell, in a battery? It happens in the anode. And yeah, so those are the things that I want you to know. Another thing, how do you read this thing? Okay, table 18.1. How do you read this thing? So really quickly, pick one, any one of these. Okay, pick any one of these reduction half reactions. Okay, I just chose that one. All right, if you want a successful battery, if you want to construct a successful battery, you need an anode, you need a cathode. You also need positive voltages. Okay, go to Walmart right now. Okay, all the batteries are running on positive voltages, not negative voltages. Okay, so you're going to pick one, and that remains the same. And what will you do to the ones below it? It oxidizes it. Very good. Okay, so this is one way you get a positive voltage. Okay, so anything below can get flipped and become oxidized, as Michael said. Okay, anything below the one you choose, we call it it. Okay, anything you choose, the one below it, can get oxidized. What about anything above it, quote unquote it? How will you get a positive voltage? Keep it the same, and what do you do to it? Flip it. Okay, so anything above gets reduced, but the one that you chose gets oxidized. Anything below the one you choose gets oxidized. The one that you choose stays reduced. Okay, so anything above, what happens? Keep it the same, reduced. The one that you choose, oxidized. Anything below the one you choose, oxidized. The one you choose, reduced. So the one you choose stays the same. Anything below it gets flipped. Anything above it stays the same. The one you choose, flipped. Those are the two ways you get a positive voltage. So that's called the diagonal rule. Okay, it determines which compound or element is better at giving electrons or taking electrons. Okay, which one of these on this list is best at taking electrons? Probably this one is really good at grabbing electrons. Okay, which is the worst at taking electrons? The absolute worst at taking electrons. Okay, the one that's negative voltage, and that's lithium. Okay, if this is the worst at taking electrons, what is it really good at? Losing or giving electrons. That is correct. Okay. So losing or giving electrons, this is really good at getting oxidized and reducing its partner. Go ahead, Michael. Yeah, it has something to do with electronegativity. That is true. Lithium, if you look in the position in the periodic table, is group 1, so it is definitely something that's not going to take electrons, but give electrons. In fact, bless you, if lithium gives an electron away, it becomes stable. It becomes stable. It becomes helium in the electron configuration. Yes, good memory. So yeah, it definitely electronegativity plays a role in it.
Is that why batteries are made with lithium? Right? Lithium ion batteries?
Yeah, lithium and something else, I don't know. I had an uncle who used to work at Energizer. This was in Alachua in the 90s, Alachua, Florida. They had a plant. So he worked a night shift. But
Alachua County?
Alachua County, yeah. But this was it was in the 90s, so 30 years ago. It's no longer there. He worked with lithium and he worked with cadmium, so yeah. So lithium batteries, cadmium batteries, I'm sure it has something to do with this. Yeah. So, this has some relationship to what you will learn outside this classroom. Okay? Electrochemistry. So this is good at giving electrons, so we say that this is very good as a reducing agent, best reducing agent ever. Okay. Why is it a best reducing agent? Because it itself is good at getting oxidized. Okay, here all the way at the top, we call it the best oxidizing agent ever. Why is that? Okay, because it gets reduced, and what will it do? What will it do to its partner? It will oxidize it. Okay, so the oxidizing agent gets reduced, and when this gets reduced positive 2.87 volts, it can oxidize. In fact, it oxidizes everything below this. It oxidizes everything in this table. So this is the best oxidizing agent. Okay, this is the best reducing agent because it itself can get oxidized, and if it does, it's positive 3.05 volts, and it reduces everything above it. In fact, it can reduce everything above this table, just like everything below this table can be oxidized by the fluorine F2 gas. Right, so this is how we read this table. Okay, so bring this to the exam and let me work and see if I can get a better copy. If not, I don't know, we'll just have to adjust. But let me work on that, making something where it's a little easier to read. If you're going to read the textbook, or if you're going to read the OpenStax or the PDF textbook, we don't have a textbook because we wanted to save students money. But you may see this in your textbook. This is not how I'm teaching it to you. I'm teaching it to you a different way. I'm having you flip one and keeping the one the same. So you may see this in your textbook, but you can refer to their interpretation, but you'll get the same answer. So check out the textbook if you want an alternative explanation, or the ebook, I should say. I think we also mentioned this rule here. If you multiply this half reaction by a number, what happens to the voltage? It does not change. Okay, so as an example shown to us on page 4. Okay, so we take this half reaction, which was taken from the table. Okay, and what I did was I multiplied it by 2. Okay, I multiplied it by 2. And not only did I multiply it by 2, but it looks like what I did was I flipped it. Okay, so first of all, by flipping it, it's no longer cathode, but what is it? Anode. And I multiplied by 2, but what has happened to my voltage? Okay, so what has only changed by flipping it? the sign. Okay, so this is very important. I've seen this 9 years here at Methodist. People will multiply this by 2. They won't change the sign. They change the actual value of this number, but the actual value of this number never changes. Okay, if you want to know the reason why, it's because this is called a state function. State function. State functions don't change. Right, so multiplying it by 2, the number stays the same. Flipping it changes the sign. It's rated. Okay, and multiplying by 2 keeps it still at 0.53 volts. So I think if you know those fundamental basics, it should be okay in terms of how to read this and how to do some of your homework problems and quiz problems. Another thing is the diagonal rule. So anything below it can get flipped. Okay, anything above it cannot get flipped. Okay, so that's the diagonal rule. All right, we went over that, and we went over this also on Wednesday. All right, now let's move on to page 6. Okay, let's go ahead and do this problem together, even though I worked it out. We'll do it together. All right. All right, it says here, what is the standard? So the word standard here means standard state. EMF is just a fancy word for voltage. Okay, it stands for electromotive force. Okay, so we're really talking about voltage. Okay, so electromotive force, voltage. Okay, they're trying to sound smart. Okay, it's the same thing. Of a galvanic cell. So what are the two parts of a galvanic cell? Anode and cathode. Of a cadmium electrode in 1 molar cadmium nitrate. So let's do the cadmium here in pink. With a chromium electrode, 1 molar, 1 molar, and it's at 25 degrees C, which gets oxidized and which gets reduced spontaneously. So when we say something happens spontaneously, we want to ensure that we're getting a positive voltage. Then and only then is this cell going to be spontaneous, which means favors the products. Okay. So we'll first use our table here, cadmium electrode. So just remember here, cadmium nitrate, it's Cd plus 2 and NO3 minus. The NO3 is a spectator ion. Okay, the cadmium is part of the electrode. And what is the half reaction for cadmium? Let's take a look here. Okay, let's have a race to see who can find it first. Oh, I found it first. All right, let's write it down. Cd plus 2 plus 2E minus is going to go to Cd solid. Okay, and what is the voltage for that? This is E cathode, and this is minus 0.40 volts. Okay, that's the cadmium electrode from here. All right, in blue we have the chromium. Where are you, chromium? This is actually Cr, if you look at the formula here, Cr plus 3 and NO3 minus is the spectator ion. So where is chromium plus 3 from the chromium nitrate? And I found this one. I am on a roll here. Nothing can stop me now in finding these things. All right, I'm going to write that as is. Okay, chromium plus 3. It's in blue. And that's Cr solid. And this also is the cathode. And this is minus 0.74 volts. Okay. Well, two things. One, spontaneous means we need a positive voltage. And two, what are the parts that make up a galvanic cell? Cathode and anode. So one of these has to be the anode, and the other one has to remain the cathode. So which one do you think you want to make the anode to make this spontaneous? That is positive voltage. The pink one or the blue one? Pink cadmium or blue chromium? Which one will be the anode? The which one? Yeah, I would flip the chromium and make it the anode. Okay, so let's go ahead and do that. I'll do that here. So I'm going to keep this one the same. Okay, this is going to be E cathode, standard state. And like Allison told us, in her mind, she's going to flip the bottom. I agree. We'll flip that one. When you flip it, what will it become? When you flip it, it will become E anode, and that's positive 0.74 volts. Running out of space. Okay. All right, and what do I need to do to cancel out the electrons? Okay, I'm going to multiply the top by what number to cancel out the electrons? What number? 3. Very good. No. Yeah. Top one by 3. You're right. And the bottom one by what? That's right. I'm going to multiply the top one by 3 and the bottom one by 2. I multiply the top one by 3. What is the voltage? Is it going to be minus 0.40 volts? Remember, these numbers do not, what? They do not change. So even if I multiplied it by 3, it's still minus 0.40 volts. Volts. And then 2Cr solid. Even though I multiplied the bottom one by 2, this still remains 0.74 volts. I flipped it though. So how many electrons are being transferred here? This is a 6 electron transfer reaction, isn't it? 6 electron transfer reaction. Which one is our anode? Okay, this one. Which one is our cathode? Cadmium. We'll add these up. The 6 electrons cancel out. This is what we want. We don't want free electrons anywhere because that's not good. It's also not good for your health. 3Cd plus 2 aqueous plus 2Cr chromium. And And this gives you 2Cr plus 3 plus 3CD solid. Okay, and then we add these two reactions. We add the corresponding voltages. Remember, this is the cathode, this is the anode, and what is minus 0.40 plus 0.74? It's positive 0.34 volts. Hey, it's positive, and that means it's a spontaneous reaction, and that is E cell. And this is the answer. So this positive 0.34 volts means it favors the products, right? Positive means this favors the products. And it means it's spontaneous, so on and so forth, okay? All right, let's do a notation here. There's a notation called the galvanic cell notation, and it goes like this. Okay, it goes like this. You're going to do the anode couple. Okay, a salt bridge. The salt bridge is 2 lines. The salt bridge is 2 lines, and then you'll do the cathode couple. So this 2 lines is called the salt bridge. Okay, so what is our anode couple here? Okay, it's going to be Cr solid. You're going to draw 1 line, and it goes to what? Cr plus 3. Okay, what's our salt bridge again? 2 lines. What's our cathode couple? CD plus 2. You're going to draw 1 line down, vertical line, goes to CD solid. Okay, the CD plus 2 is aqueous. So on an exam, or the quiz, or homework, this is equivalent to this. Okay? I mean, you can balance it, but if I give you this on the exam, you should directly get that. Okay? And if I give you the equation on the exam, you should be able to convert it to the galvanic cell notation. So be comfortable going back and forth between this notation and the actual balanced redox reaction. All right? Yes, go ahead.
Why wouldn't you put the 3 or the 2?
I think you can. There's not, yeah, you can put the 3 and the 2. I think when you deconvolute this, Asia, when you deconvolute or break it down from this to this, you're naturally going to want to balance. But I can change it so that you can put the 3 and the 2. But if you go from here, let's say I give you this on the exam, you're going to get this, and then you're going to realize, oh, I need to balance it. But I'll do that just for you. We can do 2Cr solid. I mean, what you're saying is actually a little bit more thorough, but than how I depicted it here. So, yeah, we can also put it like that, which is probably, a better way of putting it, more thorough. A good student would write this. A lazy person like me would do this. It doesn't matter. But if you're going to do it this, I want it balanced, because we should always balance our equations.
Like, when you were flipping the second equilibrium,
Second reaction.
Yeah, the second reaction. Why'd you choose the second one? Does it matter which one we choose?
I wanted it positive. If I flip this one and kept that one negative, what would happen? It would be negative. But if I flip this one and kept the top one negative, what would it be once I add them? Positive. And for something that's spontaneous, we want it to be positive. So we want to flip it so that it's this problem is asking for spontaneous. So, yeah, because it's asking for spontaneous, we have to flip one in order to get the positive voltage. If we flip this one, the top one, and kept the bottom one the same, and added them, we will get a negative voltage. Flipping the top one positive 0.40 plus a minus 0.74 would be minus. But keeping this one as a cathode, flipping it, converting this to the anode, a negative 0.40 plus a 0.7 will give you positive 0.34, which is spontaneous because it's positive. Yeah. Yeah. All right, it's a good question. And we want to flip. You got two of them. You're going to flip one. That's going to make it positive. Once you flip it, the cathode becomes the anode. Reduction becomes oxidation. All right, let's move on to page 7 here. We have some equations that I will give you on the test. So all right, I'll give you these on the exam. It's the same on the top of page 8, so they're kind of the same thing. So E cell here, this is electrochemistry, okay, generating voltages from chemicals. This is standard state. Okay. This here, delta G, is thermodynamics, telling us whether a reaction will move energetically towards the product, energetically favored or not. This is thermodynamics. Okay. And K, as you remember, is the equilibrium constant. Products over reactants. No solids or no liquids. This tells us whether in an equilibrium which is favored. Okay, is the products favored or the reactants favored? Okay, so this tells us if the products are going to, when it's all said and done, the reaction is complete, will we have more products or more reactants? The K, the magnitude of K actually tells us this. This tells us whether energy will be released or energy is required to get to products. So this will tell us whether products are favored or not. This will tell us whether energy will be released, and usually that happens when products are favored. And this will tell us if this gives us a positive voltage. If this reaction gives us positive voltage, what does that mean? It means products favored. Okay, positive voltage, products favored. Okay, high equilibrium constant, products favored. Negative delta G, products favored. Okay, so all these three come together. This is how much you have left over after the reaction is done. This is how much energy is given off after the reaction is done. And this is how much voltage or volts is given off when the reaction is done, if you're talking about batteries. So all these three are merged and synced together. Okay. Chapter 16, chapter 17, and chapter 18 all come together in these beautiful sets of equations. Okay, beautiful. I think they're beautiful, right? They're giving us 3 chapters all in one equation. Okay, what is the delta G here? That's standard state. Okay, standard state. Okay, what is the E cell here? Okay, that is standard state. Some constants I want to tell you here. F is the Faraday constant, and that's 96,500 joules over volts or coulombs over mole. Okay, I'll give you that on the test so you don't memorize it. Faraday constant F. Okay, or you may see this as 96,500 joules over volts. Okay, this is called the Faraday constant. All right, I'll give you that on the test. Okay. All right, so that's F. We have another thing here called N. N is the number of moles of electrons transferred. As an example, previous example, how many electrons were transferred? 6. This was a 6 electron transfer reaction. This was 6. So that's N. Okay? So N is the number of moles of electrons that are being transferred in the reaction. Okay, from the anode to the cathode. Okay, lose electrons, gain electrons. So N is the number of moles of electrons transferred. And R, okay, R is the gas constant, and here we're going to use 8.314 joules over moles Kelvin. So those are the constants that I will give you. And anything else here? T here is temperature. Okay, remember in our discussion of thermo, in some instances, if it's enthalpically favored, you want to lower the temperature. If it's entropically favored, you want to raise the temperature to get the products to form. So temperature is in 2 of these 3 equations. All right, I'll give you all of these three equations on the test. All right, let's move on now to page 8. All right, kind of the same thing going on here with this triangle. I want you to see this table. Let's go over this table together here. If your K is greater than 1, that means you're favoring the products over reactants. It means the delta G is negative. We call this an exergonic reaction. Exergonic. And your E cell is positive. Okay, obviously we want positive voltages if the reaction is going to favor products. Okay, so we have a reaction that favors the products. Let's say your K is less than 1. Okay, products over reactants, no solids, no liquids. If your K is less than 1, you're favoring reactants. Your delta G is positive. We call this an endergonic reaction. Endergonic. Delta G is the final judge. It takes input from entropy and it takes input from enthalpy. This is an endergonic reaction. And then your E cell, the voltage will be negative. Okay, obviously if you have a negative voltage in a reaction, if it's producing negative voltage, we're having a dead battery essentially, and products are not favored. Okay, so this would be a negative voltage. All these three just basically mean that your reaction, our redox reaction, does not favor products. It does not move forward. It stays in the reactant side. So the thermodynamics, the equilibrium of how much is left versus how much is left and how much is reacted, products over reactants. So how much reacts, the energy, and the voltage all tell us whether products are favored or reactants are favored. All right, if they all equal to 1, if K equals to 1, that means products is equal to reactants, That means your delta G is equal to 0, your E cell is equal to 0, and we basically have a situation where we are at equilibrium. Okay, under standard state. So if I were to condense this down into a nutshell, these three conditions on top represent a battery. Okay, well, some voltage, it could be small. Okay. These conditions in the second row represent a dead battery because it's negative voltage. And the situation presented by row 3 is no battery. Okay, you have no reaction, nothing. It's not a product, it's not a reactant, it's just an equilibrium reaction. And that's when your voltage is 0. Some couple of other tidying up points before we move on to the problems. The coulomb is a derived unit. 1 coulomb is equal to 1 joule over 1 volt. So maybe that's something you can keep in the back of your mind, but I think I will tell you that on the exam. And then if you plug in a couple of numbers here for the constants, if you plug in T at 298 Kelvin, that is 298, that is 25 degrees. You plug in your Faraday constant. If you plug it into these three equations in the triangle, if you plug it in, you'll get a couple of the derivations. Okay, you get a natural log form and a log form. So I'll give you this on the test, so you don't have to memorize it. Okay, in fact, that's on page 10. Right. So I'll give you these on the exam. I'm just plugging in the constants to these equations. All right, actually. All right, plugging in the constants to these equations, you'll get here and this. Okay, you'll get there's a natural log form, there's a log form, but I'll give you this on the test. Okay, you just need to know how to plug and play it. Plug and play. All right, let's go over some practice problems here. We'll try to see if we can finish this page, or at least we'll finish the first example. All right, calculate the equilibrium constant for the following reaction at 25 degrees. So we want the equilibrium constant, which is K. And the first thing we would do is, what I'd like to do is when I see this equation, I'm going to split it up. And we want the equilibrium constant K at 25 degrees. So let us, which equation shall we use? Okay. Of these three equations, I think I'm going to use this one. Okay, I'll tell you why. Calculate the equilibrium. No, my bad. Calculate the equilibrium constant. I'm going to use this equation. Okay. I'll tell you why. Okay. All right, so we want K here, which is the equilibrium constant. The first thing I'm going to do is I'm going to figure out the voltage associated with this reaction. All right, so here we have Fe plus 2 going to Fe solid. All right, how many electrons and where should I put it to balance this equation? How many electrons and where should they go? 2 electrons and where? Very good. Okay, reactant side. Okay, so this will balance out my ions and it will balance out my charge. Is this oxidation or reduction? Is this cathode or anode? Reduction, so we're going to use this table here. And what is it for Fe plus 2? I can't find it. Negative 44? I got it right here. Okay, thank you, Mike. Okay, here it is. Okay, so this is E cathode negative 44. Alright, and then we have Ag solid going to Ag plus. All right, how many electrons and where should I put them? 1, and which side, Asia? The right-hand side or the product side. Is this the cathode or the anode? Okay, this is the anode. And what is the voltage associated with that? 0.80. Did you flip it, Michael? Oh. Okay, so Ag solid, I got it here. Ag solid plus 1 electron, Ag plus 1 electron goes to Ag solid. Okay, so what do I need to do with this equation? Huh? Okay, why do I flip it? This is what I have in the problem. I have Ag going to Ag plus. So here I have Ag plus going to Ag solid. This is positive 0.80 volts. But here I have the opposite happening. So I'm going to take this value here and flip it. Okay? I'm going to take this value here and flip it because that's what's happening in my problem. And besides, if this is the cathode, what will by default this have to be? The anode. Okay, just by default, you can't have 2 cathodes or 2 anodes. One has to serve as the anode, one has to serve as the cathode. So I flip that according to this problem. That's minus 0.80 volts. And then I am going to add this up. What should I multiply the bottom one by? 2. So how many electrons are being transferred? Okay, this is a 2 electron transfer reaction. This is a 2 electron transfer reaction. So I have here, I think I'm running out of time, 2 electrons plus Fe plus 2 goes to Fe solid. That's minus 0.44 volts. This is 2 Ag solid going to 2 Ag plus 2 electrons. That is negative 0.80 volts. And then the 2 electrons will cancel. And we have 2 Ag solid plus Fe plus 2 this is going to go to Fe solid plus 2 Ag plus. Okay, what's minus 0.44 plus a minus 0.80? Minus 1.2? Minus 1.24, that's right. So minus 1.24 volts is equal to E cell. Okay, so I got E cell. Notice that I regenerated my original reaction, but this time I got my E cell here. The negative sign tells me this is non-spontaneous. And now what we will do on Monday is we will take that minus 1.24 volts E cell, and we will plug it in here and solve for K. Okay, we know R, we know T, we know F, and we know N is a 2-electron transfer reaction. So we'll take that and then solve for K, and that will give us our equilibrium constant. All right, so that is something we will do on Monday. So have a good weekend, and try to work on your 17 and 18 homework, or at least, no, your 17 homework should be already turned in.